So we'll start from yesterday's, just recap what we have done yesterday. Now, we discussed about doping. Okay, doping means addition of impurity to a pure semiconductor. Okay, this is the classification. This is the classification of semiconductors. Classification of semiconductors. So we have pure and impure semiconductor. Pure or intrinsic, that is silicon and germanium, and impure is we have p-type and n-type semiconductors. Okay. Now, one second. Now we have valence band and conduction band. So how do we form? So we need for the third group element, we have 13th group or 13th group element. So we have here boron, aluminum, gallium, indium, thallium. These are the 13th group or third group element which has 3 electrons in the valence shell. So that is also known as trivalent elements. These are the next one is 4th group elements or 14th group elements. So 4A or 14th group. In the old periodic classification table it will be 4A, but in the new one it will be showing as 14th group. So this is carbon, silicon, germanium, tin lead. So it has 4 electrons in the outermost shell, and this is also known as tetravalent elements. Next is 5th group element and 15th group element. Okay, so nitrogen, phosphorus, and arsenic, antimony, and bismuth. It has 5 electrons in the outermost shell, also known as pentavalent elements. So the first element in all the 3 groups is a gas, and last element in all the 3 is a radioactive element. So we don't consider the first and the last one. Only we will take the middle ones, okay, the center ones. So with that we try to form a compound, a semiconductor compound. So in n-type semiconductor we are taking element A, which is pentavalent. Okay, impurity, addition of impurity to a pure semiconductor is said to be doping. So we are adding A as impurity to B. So B is a perfectly, B is perfectly tetravalent, and A is pentavalent. When we add it, one extra electron is there in every combination. So due to that, what happens is number of electrons, total number of electrons will be more than the total number of holes. Whereas in p-type semiconductor, we have 4th group element, that is we are doping 3rd group element with 4th group element. So in that case, what is happening here? X is a trivalent element. So there are only 3 electrons in the outermost shell. So, and because of which what will happen? A hole is there. Okay, a hole is formed. So that is a hole is there. That is due to that what happens is p-type semiconductor, the charge carrier is hole here. Next, doping. Doping means addition of impurity to a pure semiconductor is said to be doping, and hole is vacancy part of electron. So because of which what will happen? Number of holes are more than the number of electrons in p-type semiconductor. Next one. After that, we have we have energy band diagram. So we came to know that in n-type semiconductor, how much amount of energy is required for the electron to jump from valence band to conduction band, or what is the energy gap? The energy gap is, for germanium it is 0.72 electron volt, and for silicon it is 1.1 electron volt. So mostly that is the reason why in most of the semiconductors we are using silicon. Okay, we are using silicon because it has 1.1, but very sensitive devices we use germanium, but it becomes also expensive. So we have why electronics became cheaper, because silicon is abundance in the nature. Only the money goes in purification and all those things. Okay, so fabrication and purification and all. Otherwise, silicon is very cheap. So it is abundance. Okay, so silicon, germanium is also, we are also using germanium, but very less. But silicon, it is abundance, so therefore it is 1.1 electron, and also has a more band gap also. That is 1.1 electron volt. Next one is the crystal maintains an overall charge neutrality as the charge of additional charge is just equal and opposite to that of the ionized force in the lattice. So that is the reason. So we are drawing the diagram in this way. So they are like these are the ions minus, and this plus are the ions. They are neutralized in that way. Okay, they are neutralized in that way. So now Ni is said to be number of intrinsic electrons generated. Okay, so there is an electron hole configuration. So when an electron is moving ahead, what is happening? When the electron is moving, it is leaving a hole backward. When the electron is moving forward, the hole is it is leaving a hole backward. So that is why actually holes are not moving. When the electrons are leaving forward, it is leaving a space behind, because of which only we say hole current, electron current and hole current. Now Ne is number of electrons, NH is number of holes, and majority charge carriers are electrons and minority charge carriers are holes. Now we have germanium and silicon crystals here. Next here, see here, there is a electron here. This is the core donor and this is the electron. Next one is p-type semiconductor. NH is number of holes and Ne is number of electrons. So here we have p-type semiconductor. In thermal equilibrium, what will happen? If you multiply Ne into NH, it will become equal to Ni square. Ni square, it is for intrinsic. Intrinsic means pure semiconductor. Keep that in mind. Okay. Now this type of situation happens in N-type semiconductor, and this type of situation happens in a P-type semiconductor. To understand more about the crystals and all, you should know what is the crystals. First of all, in chemistry we have crystals. Yeah, solid state chemistry, there is a chapter in chemistry. Even in physics also we have solid state physics. The same, like the types of crystals. Then we have defects, Schottky defect and Frenkel defect. You should know about that, how it is. Then only it will be easy for you to understand this electronics. Okay, but in physics, unfortunately, we don't have that lesson now. Now, going to the next one. See, these are the energy levels. When you look at the energy levels, see here, these are the energy levels now. So what happened here? These are the electrons. Okay, these are the electrons, and these are the see, this is the valence band and this is conduction band. See, once again, this is a valence band and this is the conduction band. Okay, valence band and conduction band. Energy of valence band, energy of conduction band. You know that the energy of conduction band is little higher. In conductors they overlap, but in semiconductor and insulator they don't overlap. But in semiconductor it is very close. So if we give little energy, then electron will jump from valence band to conduction band. So this level, the dotted line, is said to be Fermi level actually. That is, here he told a donor energy level. Donor energy level, because the donor is very close to conduction band. Instead of a valence band, the donor is very close to the conduction band. Okay, donor is very close to the conduction band, and the gap is said to be energy gap. And how much is that difference? Also 0.01 electron volt. Means the donor is very close to the conduction level. If you give little energy, then what will happen? The electron will easily jump. Okay. Now come to, this is at 0. We are saying when T is equal to greater than 0 Kelvin. Okay. Generally at room temperature it is pretty easier to send the electron from the valence band to conduction band. Coming to the p-type semiconductor, in p-type semiconductor there are, in valence shell there are more holes than electrons, and in conduction band there is no electrons, very few electrons, and the gap is known as energy gap. And the Fermi level, the line, the dotted line, is also known as acceptor energy level, and the value is 0.01 electron volts again. Okay, so this is the difference between a p-type semiconductor and an n-type semiconductor. Yeah. Next is a Pn junction diode. When a p-type substrate is brought very close to a n-type substrate, when a p-type substrate is brought very close to a n-type substrate, what happens? A Pn junction diode is formed. Why Pn junction diode has got a significant importance? Because it is a backbone. If you can understand Pn junction diode, you can understand Zener diode, you can understand solar cell, then LED, then photodiode. There are so many diodes. There are so many diodes. It's not only the one diode. There are so many diodes. Only in our textbook they have given only very limited diodes. And after that we have transistors. Again, in transistor there is a very big family. We have NPN transistor, PNP transistor, tunnel. Tunnel diode is there. Then we have there are different types of transistors. FET, field effect transistor, JFET, junction field effect transistor. Many transistors are there. but transistor also is removed from the syllabus this year. But so if you can understand transistor, then you will understand how the IC fabrication or IC formation took place. In one small IC of 8-pin IC, I'm speaking about 8-pin IC, the IC will be like this. IC means it has chip, what we say, 1, 2, 3, like 8 will be there, this is the thing. Okay, so there are 8-pin IC, there will be around 25 transistors in a small chip. The size of this chip is not even 1 square centimeter, or somewhere around 1 square or 2 square centimeter. Okay, and it has 8 pins, and in that we have 25 transistors. You can understand now how advanced we are working with, instruments we are working with. And also, if there is a in our computer on the motherboard, there is a Intel Core processor chip, Intel Core, like Intel, that they will be writing, no, Intel Core i5, Core i7, Core i3. There is a chip, a square. You might have seen this, a square shaped chip. Okay, a square shaped chip is there. So it is around 1 inch square, 1 square inch. You know, there are around 1 million transistors in this chip. This is the actual thing. If this is spoiled, your motherboard is gone. So there are around 1 million transistors in this one. So that is the reason our computer is so fast. It is able to take that many bits or bytes in 1 second or 1 millisecond, 1 nanosecond, whatever it is. So that's so advanced. So because to understand all these things, one should know how the junction diode works, how the transistor works. Then it will be easy to understand the bigger ones. Okay, but nowadays no one is much interested in the working. We are only fabric. We are much interested in only instrumentation, not in working of the devices. Okay, now. Here we have in Pn junction diode, P type substrate is brought very close to a N type substrate. A Pn junction diode is formed, and here we have electrons, and this is the holes. Okay, electrons and holes. So here we have electron drift. This is also electron diffusion. So electron, okay, we'll quickly see. What is diffusion? Diffusion means motion of electrons from high concentration area to low concentration area. This has more number of electrons and less number of holes. This has more number of holes and less number of electrons. Now, electrons will drift from high concentration area to low concentration area and diffuse from high to low, and electrons will drift from low to high. Means, in drifting means what? In electricity chapter, we studied that these electrons will collide with each other, and they slowly move. They move in a zigzag fashion, but finally there is some displacement that is giving rise to electron drift. Similarly here, hole drift and hole diffusion. Hole diffusion means holes are diffusing from high concentration area to low concentration area, and hole drift means they drift from low to that is low to high. It means this exact fashion same, but they don't actually move. When the electrons are moving, they leave the holes behind. That is actually happening, and this is depletion region or depletion space charge region is formed due to minority charge carriers. Yesterday I have given an example. Suppose if you make a girl sit in boys class, or if you make a boy sit in girls class, they are both not comfortable. They are not comfortable. They want to just move out of the class. Okay, so it is now a weird condition. So that is a reason. So same thing here, when you attach, they are ready to move now, but you need to apply some potential difference, so that the electrons will start moving or recombination will take place. Now, but even without applying any potential difference also, but small recombination will take place here. Now, depletion, so that region is also known as depletion region or space charge region, and also known as potential barrier. It has a small potential. Now, what is recombination? Electron will go and sit in the place of hole. That is said to be recombination. Okay, so a narrow depletion region is explained as a narrow region near the junction is depleted in mobile charge carrier. Okay, it is depleted in mobile charge carrier. So now that is known as depletion region. Next one. Any doubt? Any doubt, sir? Sayam, John? Any doubt?
No, sir.
Okay. Next, quickly moving to the barrier potential. What is the same thing? The barrier potential, due to accumulation of charges near the junction, an electric field is established. A small electric field is established. This gives rise to electrostatic potential. So that is the reason we have passive components and active components. So diodes come under active components. Even though you did not apply any potential difference, but there is a small potential developed in it because of recombination. We didn't see, we have active, we have, if you speak about passive components, we have passive components, and we have active components. So passive components may resistor, inductor and capacitor, whereas active components are diodes, transistors. Okay, these are active components. So even though you did not apply any potential difference, there is a small potential developed in it. So that is the reason they are known as active components. Okay. Now, so here, due to accumulation of charges near the junction, an electric field is established. This gives rise to electrostatic potential. Thickness of depletion region is how much? 0.5 micrometer. Now, here this is a Pn junction diode. Here this, a small potential is developed. That is known as space charge region. And this is a electron or hole, and this is a negative ion, and this is a positive ion. Okay. We have barrier potential of depletion region. Okay, this small barrier is developed here. Now, we already know again, germanium, the potential barrier, that was in electron volt. This is in volt. The potential, how much is the potential difference? Potential difference is measured in volts, not about the energy gap. Energy gap is in electron volt, 0.72 for germanium, and silicon is 1.1 electron volt. Whereas barrier potential is, when you take a diode, when you form a diode, then the barrier potential or the potential barrier is 0.3 for germanium and 0.7 for silicon. So that means you should not apply more than that means you can apply 0.7. Okay, and here you can apply 0.3, so that the junction starts working now. And this is the way of representation of a diode. Okay, and here we have that is represented. This is not required, but this is only for extra information, because there is a code printed on every diode. Like on resistor also we have color code. You know that on a resistor there is a color code. Same way on a diode, transistor, now we have numbering like code like this. So want to understand the code, we have this coding system. So the codes are given to you. Is that clear? So I think one second. We will discuss about that is working of a PN junction diode. Okay, so we know how the diode is formed and what is the diffusion process and drift process taking place in the diode. Now we'll go with the working of a diode. Working means the forward bias and the reverse bias of a diode. Okay, working means forward bias and a reverse bias. First I will try to explain with forward bias and reverse bias. Okay, or so forward bias and reverse bias. Forward bias. First we'll explain the forward bias. Okay, in forward bias, the P substrate or the P is connected to positive and N is connected to negative. I'm drawing a simple one. So P is connected to positive here like this. Positive of the cell or positive of the battery. This P is connected to positive and N is connected to negative. So N has electrons. Electrons are moving towards the electrons. See, electrons will move towards it will go here. It will go from N to P, and holes will move from P to N. Okay, holes will move from P to N. This is the thing happens in forward bias, and because of it, the depletion region will become very thin in this case. Whereas in reverse bias, what is happening in reverse bias? Same again I am drawing like this is a PN junction diode. This is P and this is N, and these are the holes. Okay, so these are the holes, and these are the electrons. So what happens in a PN junction diode if P is connected to negative and N is connected to positive? If P is connected to negative and N is connected to positive, so what will happen? Electrons will go from this one, from this end. So the flow of electrons of both are in opposite direction. Electrons and holes, they are moving in opposite direction. Okay, so what happens? That means electrons are moving away and holes are also moving away. There is no recombination taking place, because of which the thickness of the depletion region will be more. The thickness of the depletion region is more. So here, so I'll write here in forward bias. In forward bias, what is happening? In forward bias, P is connected to positive. P is connected to positive, and N is connected to negative of a battery. N is connected to negative of a battery. So we have P is connected to positive and N is connected to negative of a battery. So next is what? Reverse bias. Reverse bias. In reverse bias, what is happening? P is connected to negative. Okay, P is connected to negative and N is connected to positive. N is connected to positive of the battery. So there is said to be a reverse bias. Okay, so here when you connect a P to positive and N to negative, what is happening here? I'll draw the circuit diagram for this, for forward bias and reverse bias. Okay, so VA characteristic. So before that, let us discuss this one. So electrons cross the junction in the reverse region. So there is a here in forward bias. In forward bias, the current is known as, we have a current known as forward current. They easily the electrons easily cross the junction easily in the reverse direction, and the voltage, as the current increases with voltage, and what happens as the voltage increases, current also increases, but current is in milliamperes. Okay, current is in milliampere. In reverse bias, what will happen? As the voltage increases, current very small. And here the resistance is how much? The forward resistance, the resistance of the junction, which is the offer is this, the junction is offering a small resistance, that is equal to how much? That is equal to 10 ohms to 30 ohms only. The junction is offering a small resistance from 10 ohm to 30 ohms. So here when you are increasing the voltage, and the range should be how much here? The range should be, I'll write here better for forward bias, I'll write here. So let me write here properly. Forward bias, I'll write here. So here what is happening? As the V increases, I also increases. So that is equal to how much? That is in milliamperes. Okay, and the resistance equal to how much? The resistance offered is 10 ohms to 30 ohms only. 10 ohms to 30 ohms. That is forward bias. Now, whereas that happens in the forward bias. Now the resistance is known as, this resistance is known as forward resistance. This is known as forward resistance. The resistance is known as forward resistance, and the current is in milliamperes. Okay, 1 second. So the current is known as forward current. The current here, the current is known as, this current is also known as forward current, and the resistance is known as forward resistance, and the resistance is very small. Coming to the reverse bias. In reverse bias, what is happening? As voltage increases, very small current will flow. No, a small current does flow even now. Okay, so as V increases, current, very small current, I will write here, very small current flows, very small current flows, uh, very small, due to recombination, due to electron hole recombination, due to electron hole recombination. This happens due to electron hole recombination. Okay, this happens due to electron hole recombination. Now, how much is this? There is a small current also flows. That also due to the minority charge carriers. That also due to the minority charge carriers. Because there's no, actually they are also, when the electrons are coming, they are rejecting. Here also, no, they are not able to move. Electrons are not able to move through this barrier. Now, this current is known as reverse saturation current or leakage current. This current is known as reverse saturation current or leakage current. Reverse saturation current or leakage current. This is important. What is leakage current? When you apply voltage, when you apply the voltage in reverse bias, very small current flows. That also in how much? Microamperes. Very less current. That also due to what? Due to electron hole recombination. Electron hole recombination also due to minority charge carriers. This current is known as reverse saturation current or leakage current. And the voltage at which the diode breaks down. Now suppose what is the range? The range what we give here is the range of current voltage what to offer, means from 0.1 voltage to 1 volt only. We have to, the range which we apply for this particular diode in forward bias. Do not go more than 1 voltage. If you go more than 1 voltage, the diode will damage. But in reverse bias, the range of voltage is how much? From 0 voltage to 10 volts. We can go up to 10 volts, but do not go more than 10 volts. But even then also very small current, that is in microamperes, current will flow. Okay, and if you apply more voltage, the voltage at which the diode breaks, the voltage at which the diode breaks down. Okay, the voltage at which the diode breakdown is known as breakdown voltage. Okay, is known as xenon breakdown. Sometimes we say Zener breakdown or breakdown voltage. Okay, breakdown voltage or Zener breakdown voltage. Okay, so that is the meaning of this. So that is the meaning that happens in the forward bias and reverse bias. Now we will study about the VI characteristic of a junction diode. Okay, VI characteristic of a junction diode. Better we will